Hey everybody, this is Larry. This is, well, technically February 15th, but I'm always like a day behind because I'm doing these live, well, the day before. So I guess yesterday I forgot to say Happy Valentine's Day, but today I guess I'm saying it because it is actually Valentine's Day here in New York. It's very confusing, but the thought is still the same. Happy Valentine's Day. Hope y'all are celebrating it okay. But yeah, today I kind of just slept all day and kind of, or just, well, maybe not slept, but in my bed, because and just one day I'm laying my foot here. We'll see how it goes. No updates, which is kind of sad, but yeah. Let's take a look at today's problem. 2698. Find the punishment number of an integer. I don't know what happened to my tongue there. That's what? Anyway, okay. Given a positive integer n, return the punishment number of n. Okay. The punishment number of n is defined as sum of the square of all integers I such that, okay. Why is it called a punishment number? What is going on here? Like, I didn't even finish reading this, but like, it's just kind of confusing, isn't it? Or not even confusing, just like weird. Punishment number, what is going on? This is like very topical, I suppose. Well, we focus on punishment and not, anyway, okay. So what does that mean? All right, let's actually finish reading it. So that's what that means. Sum of the squares of all integers I such that I is from the decimal representation of I times I can partition the contiguous substrings such that the sum of the integer values of these substrings equals I. What does that mean? 981 10 times 10. Man, that is an annoyingly odd problem. But n is only 1,000, so what does that mean, right? Well, so what does 1,000 mean, right? It's an upper bound. 1,000 means that there are most 4 digits, right, in decimal. And well, we only care about decimal, so I guess it's whatever. And what does that mean? That means that when you're talking about partitions, then there are only 2 to the 3 at most where you're partitioning it, right? Because here you have four digits, 3 kind of numbers in between, and each of them you could think about as binary in terms of having a partition or not having a partition. And really, that should be it. Yeah. I think the thing about this problem is that it is also a prefix E problem. I guess it could be. You could say it's prefix sum, but it just means that you can probably hard code all 1,000 things, right? Because you try to calculate f of n for some for this f, but that's just equal to really f of n minus 1 plus I don't know if this I is good or whatever, right? And this good function is maybe that if it's good, then return I, right? So yeah, so that's really it. Actually, I think I did the math wrong. I lied on this one. But because I think I misread this the other way, as in the square root of this. But still, is the same idea, which is that, okay, given 1,000 squared is going to be 1,000,000. 1,000,000, you're going to, it's 7 digits. There's 6 thingies in between, empty spaces in between. So you have 2 to the 6, which is going to be okay, right? In the worst case. Yeah. Right, and for any number, we can do this calculation, and of course, there are only 1,000 of them. It should be okay, right? What's 2 to the 6? 2 to the 6 is nothing, right? 2 to the 6 is like 32, or 64. Sorry, right? So 64 times 1,000 is going to be okay. So that's basically the idea in terms of complexity. Yeah. So because we do see this, we do want to pre-process this, I think, in a way that you can use it across different test cases. It's not something that I like to do in Leetcode. I mean, it doesn't really apply, and well, it applies outside of competitive programming, just not in Leetcode, because in real life, you would probably just cache all these things and don't worry about implementing it live, right? Especially for up to 1,000. You can fit all the answers to 1,000 pretty easily, right? Yeah, I mean for sure. Sorry, I got distracted. I think it's supposed to sum up the i's, but apparently sum up the I times i's. Okay, that's fine. I mean, It's really not that much of a difference. But yeah, so we can just really do right from 1 to n inclusive. So then if good of I, then I don't know, total I return total, right? And here we can just, I mean, this is a function that does not depend on the input, right? That's what I want to say. And because it does not depend on the input, you can actually cache it, right? Or memorize it, to be more specific. I guess, I don't know, depends how you want to say it. It just means that if you're given the same number twice, you will not need to do it twice. And of course, like I said, you could actually prefix this loop, but prefix sum this loop, but is that, you know, at most you're doing 1,000 loops, so I don't know, I'm not worried about it yet. If it times out, then we'll think about it, right? So here again, there are a couple of ways you can think about this, but it's really not the way to think about it is what I said, but it really is not a big deal with respect to yeah, right? So basically you have yeah, so times x, right? And then now how do you want to write it? Yeah. The partition, I mean, because I mean, it's actually pretty straightforward to write it in bitmask, but I feel like if I write it in bitmask, I have to explain it, which is why I'm a little bit lazy. But that's okay. Yeah, I mean, I guess you can also convert it to a string. It's not really that much of a difference, right? And then now you can just do it one at a time, one character at a time, right? So you have a thing, right? Maybe index, and then the current sum, and then the current pending number, right? Something like that. And then here we're going to do yeah. Yeah, yeah, which is that return calc 0 0 0, right? Pretty straight. I mean, okay. And index is the index on the s, which is the square root or the square thing that we're doing. Current is the current prefix that we're looking at, and current sum is just the sum of the stuff that we have already done, right? So here, if index is equal to length of s, then we just if current is so we run out, then actually current sum we just add it by current. If current, or we just then return current sum is equal to I guess yeah, I guess right, maybe I don't know, something like that, right? Because current is going to be maybe it'll be more clear, hopefully anyway, as I write more. But this is the base case where okay, we ran out of digits. We add them because you can think about it just having one divided at the very end. And if this is equal to s, it's supposed to go to s or x. Okay, I think this is fine. Okay, then yeah, now we only have two cases with plus one where we write. So this is almost like take no take, right? Take no take. So take, that means that we, yeah. So then current is going to be 0 because now we have a new thing. Current sum we added. Well, let's actually shift and add first. So current is equal to current times 10 plus int of s sub index, right? I don't know how okay, right? So you shift, and then now this is going to be and then no take. That means that we continue to shift. So then now we have current and current sum, right? Oops. And then now this is a boolean, right? Meaning that we're able to reach this or not. So we just have to return. So here we can, if this is true, then return true. and then just return this as a base case. And the reason why you could, I guess actually, okay, fine. I just thought this was a little bit clearer, but you can write this as well, and it'll also early terminate, which is the key part about it, right? I thought the other way was a little bit clearer. Maybe not. I don't know. Anyway, let's give it a spin. Oh, the other one. Right, and apparently it is way too high. All right, let's see. What am I doing wrong? 1, 2, 2. Maybe I'm misunderstanding this. This looks right in the sense that 2 times 2 is 4, and then 4 can be. Is it I or maybe I did misread it? Oh, it is. For some reason, I thought I read this incorrectly. Okay, so I mean that's not bad. It's just fixing one character. I just misread it. Okay, yeah. But also that means that I do not need this. Maybe I lied. Where do I need it? Oh, yeah. Right. Let's get rid of the print statement. Oh, I'm so tired. Maybe I need more. Okay, yeah, looks good for here. I mean, I guess there is an obvious cases to test, which is 1,000, right? So we might as well just give it a spin. And it looks okay for that, so I'm not going to complain. Let's give it a submit. Still pretty fast. Like I said, you could do more caching things if you like, but I guess for this one, it's not a big deal. But yeah, what's the complexity here, right? Depending on how you want to say it, because we do amortize this a little bit. This is why this is a little bit faster. But for each number, it is going to be 2 to the d, where d is the number of digits, right? And keeping in mind that the input is represented as 2 to the d as well, which is the number of numbers representing the digits, right? Or that can be represented with the digits. For example, what I mean by that is that if n is equal to 1,000, then it takes 10 bit. Your input size is actually 10, not 1,000, right? So then you analyze your complexity with respect to that, and given that this is actually exponential. Well, I mean, this loop is exponential, and this is exponential. So this is actually going to be like 2 to the 2 to the n or something. Oh, sorry, 2 to the 2n is that the complexity. But given that n is 10 for 2 to the 10, this is clearly fine. But yeah, that is all I have for this one. Let me know what you think. Thanks for watching. And yeah, stay good, stay healthy to your mental health. Have a great weekend, everybody. I'll see y'all later and take care. Bye-bye.